Hydropower. Harnessing the energy of water. Part 1. Introduction to hydropower. What is hydropower? Hydropower, also known as hydroelectric power, is a form of renewable energy that harnesses the kinetic energy of flowing or falling water to generate electricity. As one of the oldest and most widely used forms of renewable energy, hydropower plays a significant role in the global energy mix due to its reliability, efficiency, and minimal greenhouse gas emissions. Historical background. The use of water for mechanical energy dates back thousands of years. Ancient civilizations, including the Greeks and Romans, utilized water wheels for grinding grain and irrigation. The advent of modern hydropower began in the late 19th century, with the development of hydroelectric generators. In 1882, the world's first hydroelectric power plant began operating in Appleton, Wisconsin, USA. Since then, hydropower has evolved significantly, contributing to industrialization and economic development worldwide. Importance of hydropower. Hydropower offers several advantages. Renewable and clean, it uses water, a renewable resource, and emits no direct pollutants or greenhouse gases. Reliable and efficient, hydropower plants have high efficiency rates and can provide base load and peak load electricity. Energy security, it contributes to reducing dependence on fossil fuels and enhances energy security. Storage and flexibility, reservoir-based systems can store water, enabling electricity generation when needed and supporting grid stability. Types of hydropower systems. Hydropower systems vary based on the scale and design. Major types include impoundment reservoir systems, utilize a dam to store river water in a reservoir. Run-of-river systems, use the natural flow of rivers without large reservoirs. Pumped storage systems, operate like batteries, storing energy by pumping water to a higher elevation for later use. Global hydropower capacity. Hydropower accounts for about 16% of the world's electricity generation and over 60% of all renewable electricity. Countries like China, Brazil, Canada, the United States, and Russia are leading producers. As of 2024, global installed hydropower capacity exceeds 1,300 gigawatts, demonstrating its major role in the energy landscape. Challenges and future prospects. Despite its advantages, hydropower faces challenges such as environmental impact, potential effects on river ecosystems, fish migration, and sediment flow. Social issues, displacement of communities due to dam construction. Climate change, altered rainfall patterns and glacial melt can affect water availability. Nevertheless, advancements in small-scale hydro, modernization of aging plants, and improved environmental practices offer promising prospects for the future of hydropower. Part 2. Working principles of hydropower. The science behind hydropower. Hydropower generation is based on the conversion of the potential energy of stored or flowing water into mechanical energy, and then into electrical energy using turbines and generators. The process utilizes the gravitational force of water falling from a height or moving through a river system. Key components of a hydropower system. A typical hydropower plant consists of the following main components. Dam creates a reservoir to store water and provides the necessary head-height difference to generate energy. Reservoir stores water for consistent flow regulation and energy generation. Penstock, a large pipe or tunnel that carries water from the reservoir to the turbines. Turbine converts the energy of falling or flowing water into rotational mechanical energy. Generator converts mechanical energy from the turbine into electrical energy. Transformer increases the voltage of the generated electricity for efficient transmission. Outflow tailrace returns the water back to the river or downstream area after it passes through the turbine. Energy conversion process. The energy conversion process occurs in three main steps. Potential to kinetic energy. Water held in a reservoir has stored potential energy. When released, it flows through the penstock, gaining kinetic energy. Kinetic to mechanical energy. The flowing water hits the turbine blades, causing them to rotate. Mechanical to electrical energy. The rotating turbine drives the generator, which produces electricity through electromagnetic induction. Types of turbines. The type of turbine used depends on the head and flow rate. Impulse turbines, e.g., Pelton wheel, suitable for high head and low flow conditions. Autojets strike the turbine buckets. Reaction turbines, e.g., Francis Kaplan, used for medium to low head with varying flow rates. These operate submerged in water and rely on pressure differences. Efficiency of hydropower systems. Hydropower systems are among the most efficient methods of generating electricity, with conversion efficiencies often exceeding 90%. This is significantly higher than fossil fuel power plants, which typically operate at around 35 to 45% efficiency. Control and monitoring. Modern hydropower plants are equipped with automation systems, sensors, and remote monitoring tools to optimize performance, manage water flow, and ensure safe operation. Real-time data analytics enhance efficiency and predict maintenance needs. Seasonal and climatic considerations. The availability of water flow is influenced by seasonal rainfall and snowmelt, droughts and flooding, climate change effects on precipitation and glacial sources. Hydropower planners must consider long-term hydrological data and develop storage or backup systems to ensure year-round generation. Part 3. Types and classifications of hydropower plants. Hydropower plants are categorized based on various factors such as size, design, water source, and operation mode. Understanding these classifications helps identify the best applications for specific environmental and geographical conditions. Classification by size. Hydropower plants can be classified into the following categories based on their power generation capacity. Large hydropower capacity, more than 100 megawatts. These are massive installations often associated with dams and large reservoirs. They contribute significantly to national grids. Medium hydropower capacity, 10 megawatts to 100 megawatts, serve regional or local grids and may have moderate environmental impact. Small hydropower SHP capacity, 1 megawatt to 10 megawatts, ideal for rural electrification and decentralized energy supply. Mini hydropower capacity, 100 kilowatts to 1 megawatt, suitable for small communities or isolated industries. Micro hydropower capacity, up to 100 kilowatts, designed for individual households or remote villages. Classification by design. Run-of-river ROR plants. These systems use the natural flow of a river without large storage. A portion of the river's water is diverted through a channel or penstock to the turbines and returned downstream. Advantages: minimal environmental impact, lower cost. Disadvantages: dependent on seasonal flow variations. Reservoir storage-based plants. These use a dam to create a reservoir, storing water for consistent energy generation. Advantages: reliable power supply, flood control, water storage. Disadvantages: high construction cost, significant environmental and social impact. Pumped storage plants. These work by pumping water from a lower reservoir to a higher one during periods of low demand. During peak demand, the stored water is released to generate electricity. Advantages: grid stability, energy storage solution. Disadvantages: high capital investment, site-specific. Classification by head. Head refers to the vertical distance the water falls, which determines the amount of energy available for conversion. High head, above 100 meters. Uses Pelton turbines. Medium head, 30 to 100 meters. Uses Francis turbines. Low head, below 30 meters. Uses Kaplan turbines. Classification by purpose. Hydropower plants are also categorized based on their primary function. Base load plants operate continuously and supply consistent power. Peaking plants operate during high demand periods. Pumped storage plants function as energy storage systems. Hybrid and emerging hydropower systems. Modern developments are introducing hybrid systems. Hybrid solar hydro plants combine photovoltaic and hydropower systems for improved reliability. Floating hydropower turbines placed in open-flowing water bodies without dams. Tidal and wave-driven hydro uses oceanic movements discussed more in marine energy contexts. Part 4. Design and construction of hydropower projects. Designing and constructing a hydropower project is a complex multidisciplinary process that requires careful planning, environmental assessment, engineering precision, and community engagement. This part outlines the critical stages and components involved in the successful development of a hydropower plant. Preliminary assessment. Before initiating a project, a detailed feasibility study is conducted to evaluate site selection, availability of water flow, head height, geological stability, and access to infrastructure. Hydrological survey. Analysis of river flow, rainfall data, seasonal variability, and long-term water availability. Environmental and social impact assessment (ESIA). Identification of potential impacts on ecosystems and communities. Technical design parameters. The design of a hydropower plant includes several key technical aspects. Hydrology and flow estimation. Flow duration curves (FDCs) and hydrographs help determine the energy potential. Design flow is selected based on river discharge data and desired capacity. Head measurement. The vertical drop, gross head, between the water source and the turbine is calculated along with head losses in the penstock to determine the net head. Capacity determination. Using the formula power kW equals 9.81 times Q times H times eta 1000 power kW equals 10,000 and 9.81 times Q times H times eta, where QQ equals flow rate cubic meter per second, HH equals net head m, E equals efficiency of the system. Civil works. Dam and reservoir. Designed to store water and regulate flow. Includes spillways to handle excess water and prevent flooding. Intake structure. Controls water entry and includes screens to filter debris. Penstock. High-pressure conduits that direct water to turbines. Requires strong material, steel concrete, to withstand pressure. Powerhouse. Houses the turbines, generators, control systems, and auxiliary equipment. Designed for ease of maintenance and safety. Tailrace. A channel that safely returns water to the river downstream. Mechanical and electrical equipment. Turbines and generators. Selected based on head and flow conditions. Pelton Francis Kaplan. Must be matched for optimal efficiency. Control systems. Automated systems for gate operation, turbine speed regulation, voltage control, and safety mechanisms. Transformers and switchgear. Step-up transformers increase voltage for transmission. Switchgear ensures safe and stable electricity flow. Construction phases. Site preparation, land clearing, access roads, worker facilities. River diversion, temporary structures like cofferdams to redirect flow. Dam and civil structure construction, sequential construction of dam intake, penstock, and powerhouse. Equipment installation, fitting turbines, generators, control systems. Testing and commissioning, system testing to ensure operational readiness. Grid connection, linking to local or national electricity networks. Challenges in construction. Geological surprises, unstable soil or rock can increase cost. Weather delays, rain and floods can disrupt timelines. Logistical issues, transport of heavy machinery to remote sites. Community concerns, displacement or ecological disturbances. Sustainable construction practices. Use of environmentally friendly materials. Minimizing habitat disruption and ensuring fish migration paths. Creating community benefit plans and stakeholder engagement strategies. Part 5. Environmental and social impacts of hydropower. Hydropower is widely recognized as a clean and renewable source of energy, yet its development can have significant environmental and social consequences. Understanding these impacts is crucial for sustainable project planning and implementation. Overview of environmental impacts. Ecosystem alteration. Aquatic ecosystems. Dams and reservoirs can disrupt riverine ecosystems by altering water flow, temperature, and sediment transport. Fish migration. Dams act as barriers for migratory fish species such as salmon, affecting reproduction and population levels. Habitat loss. Reservoir creation can flood forests, wetlands, and other habitats, leading to biodiversity loss. Water quality. Stratification. Water layers with different temperatures and oxygen levels can form in reservoirs, affecting aquatic life. Eutrophication. Accumulation of nutrients in stagnant water can lead to algal blooms and reduced oxygen levels. Greenhouse gas emissions. While hydropower has low emissions during operation, methane and carbon dioxide can be released from decomposing vegetation in reservoirs, especially in tropical areas. Social impacts. Displacement of communities. Involuntary resettlement. Large-scale projects may require relocation of entire communities, disrupting lives and livelihoods. Loss of cultural heritage. Sacred sites and historically significant areas may be submerged or damaged. Impact on livelihoods. Agriculture and fishing. Altered water availability can impact farming and local fisheries. Access to resources. Communities may lose access to forests, grazing lands, and freshwater. Mitigation measures. Environmental mitigation. Fish passages and ladders enable fish to migrate around dams. Environmental flows. Maintain minimum river flows to sustain downstream ecosystems. Sediment management. Regular flushing or bypass systems to reduce sediment buildup. Social mitigation. Resettlement planning. Ensure fair compensation, housing, and livelihood restoration. Community participation. Involving affected people in planning to address concerns and enhance local benefits. Benefit sharing. Providing electricity, infrastructure, or revenue-sharing mechanisms to local communities. Regulatory framework and compliance. Environmental impact assessment (EIA), mandatory in many countries to evaluate and address potential project impacts. Social impact assessment (SIA), identifies and mitigates effects on people and communities. Monitoring and reporting. Continuous environmental and social monitoring is required to ensure compliance with laws and standards. Role of international guidelines. Organizations such as the World Bank, International Hydropower Association (IHA), and International Finance Corporation (IFC) have developed sustainability guidelines including Hydropower Sustainability Assessment Protocol (HSAP), a tool to measure the sustainability of hydropower projects. Equator Principles, risk management framework for determining environmental and social risk in project finance. Balancing development and sustainability. Hydropower projects must strike a balance between energy generation and ecological and social integrity. This can be achieved by prioritizing low-impact designs like run-of-river systems, modernizing existing infrastructure instead of building new dams, Integrating renewable technologies, e.g., solar hydro hybrids, to reduce reliance on large-scale water storage. Part 6: Hydropower and Climate Change. Hydropower plays a dual role in the global response to climate change. It contributes to the reduction of greenhouse gas emissions by replacing fossil fuels, but it is also vulnerable to the changing climate. This part explores both the mitigating and adaptive aspects of hydropower in the context of climate change. Role of hydropower in climate change mitigation. Low-carbon electricity generation. Hydropower produces electricity with minimal direct emissions. By displacing carbon-intensive fossil fuels, it significantly contributes to reducing global greenhouse gas (GHG) emissions. Life cycle emissions. Hydropower plants emit between 1 to 30 grams of CO equivalent per kilowatt-hour, compared to coal 800 to 1,000 grams per kilowatt-hour, or natural gas 400 to 500 grams per kilowatt-hour. Long operational lifespan. With lifespans exceeding 50 years, hydropower offers long-term low-carbon energy. Energy storage and grid support. Hydropower, particularly pumped storage, supports other renewable sources like solar and wind by providing backup and balancing power. Frequency regulation. Fast response reserves. These capabilities enable greater integration of intermittent renewables into power systems. Climate change impacts on hydropower. Altered precipitation patterns. Changes in rainfall distribution, snowpack levels, and melting glaciers affect river flows and water availability. Increased variability. Droughts and floods impact both run-of-river and reservoir-based systems. Glacial melt initially increases water flow, but long-term reduction threatens hydropower potential in glacier-fed regions. Temperature rise. Higher evaporation rates reduce reservoir levels. Thermal impacts influence turbine efficiency and aquatic ecosystems. Extreme weather events. Flooding can damage infrastructure. Sedimentation. Increased erosion leads to sediment buildup, reducing reservoir and turbine efficiency. Climate resilience strategies for hydropower. To adapt to climate uncertainties, hydropower projects must incorporate resilience strategies. Improved forecasting and modeling. Use of hydrological models and climate data to anticipate water availability. Scenario planning for water resource management. Design adaptations. Flexible turbines designed to operate across wider flow ranges. Spillway sizing adjusted for changing flood magnitudes. Sediment control structures reduce the impact of increased erosion. Integrated water resource management (IWRM). Coordinates use of water across sectors: agriculture, drinking water, energy. Balances ecosystem needs with energy generation. Opportunities for climate finance. Hydropower projects can access international funding mechanisms if they demonstrate climate benefits. Green Climate Fund (GCF). Climate Investment Funds (CIF). Carbon credits and offsetting schemes. Projects must show sustainable practices, social inclusivity, and climate resilience to qualify. Case studies. Norway. With 99% of its electricity from hydropower, Norway exemplifies climate-friendly energy development. The country is modernizing older plants to improve efficiency and resilience. Himalayas. In glacier-fed basins, hydropower faces long-term risks from retreating glaciers and seasonal flow shifts. Projects in Bhutan and Nepal are investing in adaptive design and diversified energy mixes. Part 7: Economics and Financing of Hydropower Projects. Hydropower is capital-intensive, but once operational, it offers low-cost, reliable electricity over a long period. This part explores the economic aspects of hydropower development, including costs, financing models, and investment challenges and opportunities. Economic characteristics of hydropower. High upfront costs. Capital costs include land acquisition, civil works, dams, tunnels, electromechanical equipment and transmission infrastructure. Cost range. Typically between $1,000 to $5,000 per kilowatt kW installed capacity depending on location and scale. Low operating and maintenance (O&M) costs. O&M costs are relatively low compared to fossil fuel plants. Hydropower plants have long lifespans, often exceeding 50 years, with some operating beyond 100 years. Long payback periods. Due to high initial investment, hydropower projects may require 15 to 30 years to recover costs, especially without subsidies or favorable tariffs. Cost components of a hydropower project. Revenue models. Power purchase agreements (PPAs). Long-term contracts where utilities or governments agree to buy electricity at pre-negotiated rates. Feed-in tariffs (FITs). Guarantee fixed prices for renewable electricity, encouraging investment and reducing financial risk. Market-based pricing. In liberalized electricity markets, hydropower can earn revenue by selling power during peak demand hours. Financing sources. Public funding. Government-led investments through state-owned utilities or development agencies. May include sovereign guarantees and low-interest loans. Multilateral and bilateral finance. Institutions such as World Bank, Asian Development Bank (ADB), African Development Bank (AFDB), Green Climate Fund (GCF). Provide concessional loans, grants and technical assistance. Private sector investment. Independent power producers (IPPs) often finance small and medium projects. Public-private partnerships (PPPs) share risk between public and private entities. Climate finance and carbon credits. Hydropower projects with demonstrable climate benefits can access Clean Development Mechanism (CDM), Verified Carbon Standard (VCS), Results-Based Climate Finance (RBCF). Risk factors and mitigation. Economic benefits of hydropower. Energy security reduces dependency on fuel imports. Job creation generates employment during construction and operation. Grid stability enhances reliability of power supply. Multipurpose use supports irrigation, flood control and recreation. Case study: the Belo Monte Dam, Brazil. Capacity 11,233 megawatts. Investment approximately 16 billion United States dollars. Challenges: high environmental and social costs, but contributes significantly to national grid and peak energy demand. Part 8: Global trends and future outlook for hydropower. Hydropower remains a cornerstone of the global energy mix, particularly in the shift towards sustainable and resilient energy systems. This part examines current global trends, regional developments, technological innovations, and the future outlook for hydropower. Global status of hydropower. Installed capacity. As of 2024, global installed hydropower capacity exceeded 1,400 gigawatts, making it the largest source of renewable electricity. Hydropower generated over 4,300 terawatt-hours annually, around 16% of global electricity, and nearly 60% of renewable electricity. Leading countries. These countries are leading in both large-scale hydropower and modernization of existing assets. Emerging trends. Modernization of existing infrastructure. Upgrading turbines, generators and control systems can boost capacity and efficiency without new dam construction. Digitalization and automation enhance plant management and monitoring. Pumped storage expansion. Demand for grid flexibility and energy storage is fueling a resurgence in pumped hydro storage. Provides backup for intermittent renewables like solar and wind. Small and micro hydropower growth. Used for off-grid electrification, especially in remote and rural areas. Modular, scalable systems with minimal ecological impact are gaining popularity. Hybrid renewable systems. Integration of solar hydro, wind hydro, and floating solar on reservoirs increases reliability and utilization of shared infrastructure. Regional developments. Africa. Huge untapped potential, particularly in the Congo, Nile, and Zambezi basins. Projects like Inga 3 in the DRC and Grand Ethiopian Renaissance Dam, GERD, aim to transform regional power supply. South Asia. Himalayas offer vast hydropower potential. India, Nepal, and Bhutan are developing cross-border electricity trade through hydropower cooperation. Latin America. Hydropower dominates electricity generation in Brazil, Colombia, and Peru. Increasing focus on climate-resilient designs due to extreme weather patterns. Europe. Focus on refurbishment and pumped storage to stabilize grids with high renewable penetration. Switzerland, Austria, and Norway are leaders in pumped hydro systems. Technological innovations. Variable speed turbines. Allow greater flexibility in operation under fluctuating water flows and grid demands. AI and big data. Used for predictive maintenance, flow forecasting, and real-time performance optimization. Low head and kinetic technologies. Expand access to untapped riverine energy with minimal infrastructure needs. Challenges ahead. Climate change alters hydrological patterns, threatening reliability in some regions. Environmental concerns require robust impact mitigation and stakeholder involvement. Financing and policy support, essential to balance environmental, social, and economic priorities. Future outlook. Hydropower is expected to play a stabilizing role in grids with high renewable penetration. Become more adaptive and resilient through innovation and modernization. Expand in developing regions where electrification and water security are critical. The International Energy Agency (IEA) projects that hydropower capacity could grow by 230 to 300 gigawatts by 2030, with most new additions coming from Asia, Africa, and Latin America. Hydropower's future lies in smart integration with other renewables, sustainable practices, and inclusive development. As the world transitions to a low-carbon energy system, hydropower will continue to serve as a vital backbone of clean, dependable power. Part 9. Policy and Regulatory Frameworks for Hydropower Development. The successful development of hydropower projects depends not only on technical and financial considerations, but also on enabling policy and regulatory environments. This part explores the legal, institutional, and policy frameworks that support sustainable hydropower development around the world. Importance of policy and regulation. Effective policies and regulations ensure that hydropower projects are economically viable, minimize environmental and social impacts, align with national energy goals, receive public acceptance and investor confidence. Key policy instruments. National energy policies. Many countries include hydropower in their national energy strategies due to its reliability, renewability, and low emissions. Policies may include renewable energy targets, hydropower-specific development plans, grid integration policies, licensing and permitting. Developers must obtain various permits. Water use rights. Environmental and Social Impact Assessment (ESIA) approvals. Construction and operational licenses. These processes ensure compliance with environmental, social, and safety standards. Tariff policies and incentives. Feed-in tariffs fixed payments for electricity from renewable sources. Power purchase agreements (PPAs), long-term contracts providing revenue certainty. Tax incentives, reduced import duties, accelerated depreciation or tax holidays. Regulatory bodies and institutions. Energy regulatory commissions, set tariffs, monitor compliance and resolve disputes. Environmental agencies, oversee environmental compliance and biodiversity protection. River basin authorities, manage water resources to balance competing uses. International guidelines and standards. Hydropower Sustainability Assessment Protocol, HSAP. Developed by the International Hydropower Association, IHA, HSAP is a tool to evaluate the sustainability of hydropower projects across multiple dimensions, including environmental and social performance, governance, technical planning, World Bank and IFC performance standards. International financiers require adherence to strict environmental and social safeguards, such as free, prior and informed consent (FPIC), resettlement action plans (RAPs), grievance redress mechanisms. The Equator Principles, adopted by financial institutions to ensure that projects are developed in a socially responsible and environmentally sound manner. Policy challenges. Inconsistent regulatory frameworks. Lack of clarity or overlap among agencies can lead to delays and increased costs. Inadequate environmental governance. Weak enforcement of environmental and social safeguards can damage ecosystems and communities, undermining project legitimacy. Balancing competing water uses. Hydropower competes with agriculture, urban consumption and ecosystem needs, requiring integrated and participatory water governance. Best practices for policy and regulation. Integrated energy and water planning, align hydropower with water resource management. Stakeholder participation, ensure local communities, indigenous groups and NGOs are included in the planning process. Transparent and predictable licensing, streamlined and consistent approval processes increase investor confidence. Adaptive management, allow policies to evolve with climate science, hydrology and stakeholder feedback. Case study: Norway. Norway has developed one of the most mature regulatory frameworks for hydropower, balancing rigorous environmental assessments, public engagement, revenue sharing with municipalities, continuous modernization of legacy infrastructure, role of international cooperation, transboundary water treaties essential for shared river basins, e.g. Mekong-Nile, technology transfer, shared expertise and innovation help developing countries implement sustainable projects. Capacity building, international support for training and institutional strengthening. The way forward. A robust, transparent and inclusive policy environment is key to unlocking hydropower's full potential while safeguarding ecosystems and communities. Governments must promote green investment frameworks, enhance institutional capacity, foster public-private partnerships, harmonize energy and environmental policies for long-term sustainability.